Today, for whatever reason, my iPad's not charging, so we're going to have to do this the old-fashioned way with some board work here, looking at these slides. I'm going to substitute this chapter. I don't like your textbook slides, so I'm going to substitute it with a bit of my own slides here. Nonetheless, today we're talking about aromatic compounds. Okay, so we're going to continue our discussion. We're going to introduce this new functional group. These are a class called aromatic compounds. And the quintessential example of the aromatic compound is benzene. Okay, that's like kind of the classic one that everybody thinks of when they think of aromatics. So we'll talk about what it means to be aromatics and how we classify things as aromatics. But let's take a look at benzene here for a second and see if we can convince ourselves as to why it's so special here. So again, benzene, right? You got a ring. Every other bond is a double bond, okay? When you have this perfect spacing like this, double bond, single bond, double bond, single bond, double bond, single bond, this is what we call conjugated. In this case, it's a ring. Conjugated double bonds, a conjugated ring, okay? What makes this so special is that these electrons in these double bonds here, they're not actually like stationary within this position. Okay? They can actually flow all the way around this ring. They're kind of constantly moving around this ring here. This is something that really tripped scientists out for a while because, prior to quantum mechanics, the world was neatly split into particles and waves, right? Early physicists thought, they knew light was made of waves, and they thought all atoms were made of particles, and the universe was neatly divided like that. And it wasn't until like the 1920s came around that there was this theory of quantum mechanics that said, well, actually everything behaves a little bit like a wave and a little bit like a particle. And so it turns out that this is a good example of electrons behaving like waves. They're not stationary particles that sit in one place. They're actually kind of diffuse around this whole ring. And it's not like they're kind of like just stationary little marbles spinning around and around. They're spread out all at once, right? So we kind of think of electrons now as being more like clouds. And this cloud can kind of diffuse itself all the way around this ring. So again, something that like really didn't make sense early on in the history of chemistry, but kind of like made sense once quantum mechanics was introduced. All right, so why the hell is that? So if we go back to what a pi bond actually looks like. Right, remember we were talking about double bonds. When we were talking about alkenes, so this structure here, this little cloud structure here is just this molecule, right? And we talked about how the first bond, one of those bonds, is just a normal old, what we'd call sigma bond, where the electron density sits between those two atoms, kind of like what you would expect for a bond. The electrons that are being shared are just directly between those two atoms. But that second bond is what we call a pi bond, and that's kind of weird. It's got this electron density that sits up in a cloud both above and below those atoms, right, in these weird peanut-shaped orbitals here. So this is what a pi bond is, that second bond, all right? So if we looked at each of these carbon atoms here and kind of like pictured, I'm going to try to draw it on there, good luck for me, but drawing these sort of peanut-shaped things, each one of these carbons has that kind of peanut-shaped orbital going on. Right? And as what's pictured here with this double bond, that means that these orbitals are mixing, these orbitals are mixing, and these orbitals are mixing. Right? But you have this perfect line of all these little peanut shapes all in a row. So again, the electrons don't stay here. They kind of diffuse all the way around, spread themselves out all the way around this ring. This is this concept of aromaticity, this idea of delocalized electrons. Not, right, let's just pick that word apart, delocalized, as opposed to localized, localized meaning they're staying still, delocalized meaning they're spreading out. So an aromatic compound has electrons that are being spread out throughout a ring. All right, so again, benzene's the classic example. We'll see some other molecules as well that behave as aromatic. But it's this idea that you have these peanut-shaped orbitals, and they're all sitting in a line that allows the electrons to diffuse all throughout that ring. It turns out that that really helps to stabilize this molecule. Benzene is a remarkably stable molecule. It's fairly unreactive, all things considered. So for whatever reason, there's this magical stabilization effect of aromaticity. They don't sort of like have as much energy as you would expect based on, you know, the number of bonds and all that good stuff. Okay, so bottom line is when we think aromaticity, we're going to think a magically stabilizing effect here. And we're going to see because of that, even though these have double bonds, they do not behave like normal alkenes. Right? In the last chapter, we learned of a bunch of reactions of alkenes. Benzene does not share those same reactions. Its double bonds are not as reactive because of that magical stabilization effect. Okay, whoops. I'm not going to worry about benzene nomenclature because, quite frankly, I hate it. So we're going to just gloss over the nomenclature portion of this chapter here. The bottom line is that the benzene is kind of the parent chain, but the real pain in the ass is that they are a lot of special little functional groups, and they have their own name associated with them. So a benzene with an alcohol group gets its own special name. It's phenol. Benzene with a carboxylic acid group gets its own name. So it just kind of complicates things in a way that we're going to sort of gloss over here. Okay, so if we are ever talking about benzene names and stuff like that, you'll get like a cheat sheet or something, but it's not something I'm going to quiz you on. One important functional group that we're going to see play a prominent role in this particular chapter that we haven't talked about at all is what's called a nitro group. All right, so nitrobenzene is something we're going to see sort of over and over again. So we need to take a look at this nitro group here. All right, so the nitro group. Of course, you can draw it kind of in that condensed way. Just NO2, and that's all well and good. I already lose a pen? Oh, okay. All right, but, and importantly, because in your homework you're going to have to, you want to be able to draw sort of the full Lewis structure of it as well. And so what that looks like is the nitrogen has a single bond to one of these oxygens. If it has one bond, how many lone pairs does it have? I guess I just put it up there. 3, and then so what's the formal charge on this oxygen? -1. This oxygen has 2 double bonds, so how many lone pairs? 2. And then what's its formal charge? 0, so I don't have to write anything. So the nitrogen in the middle has 4 bonds, so how many lone pairs? 0, and then what's its formal charge going to be? +1. So this is kind of this weird functional group where you have a nitrogen with a +1 charge, but then an oxygen with a -1 charge, so they cancel out. So the net charge here is 0, which is why you don't see a net charge written in the condensed form here. But if we're going to draw out the actual Lewis structure for it, we need to make sure to include the formal charges on those 2 atoms. Okay, so again, that's something that you're going to be expected to be able to do. Oh, there it is. All right. So we'll see why this is important here in a second when we talk about sort of reactions of benzenes, but this is something brand new that we haven't seen before. So again, this is called a nitro group, and we want to be able to sort of draw it full out here in terms of its Lewis structure. So again, the nitrogen has a positive charge, the oxygen has a negative charge. One of the oxygens has a negative charge. Okay. So we're going to skip nomenclature. We're going to talk about this concept of aromaticity. So what is it that makes a molecule aromatic? We got some rules. There's really only like 2 rules that we got to learn here. All right? Yeah, we can skip over. Historically, I'll say, historically the benzene really bugged everybody out because, again, they sort of, early on, we had a way of figuring out what the formula of a molecule was. So they knew that it was C6H6. So everybody convince yourself that indeed looking at this bond line structure here that there are 6 carbons, right? And each carbon will only have 1 hydrogen attached because it already has 3 bonds explicitly drawn. Okay, so the formula would be C6H6. So they knew that. They knew it was a ring. And they knew it was like this perfectly symmetric molecule. And that was really bothering them for a long time because double bonds are supposed to be shorter than single bonds. So it should be this like weird shaped molecule, not perfectly symmetrical. And that wasn't until they realized that these electrons can, again, be in more than one place at once. So if we were really going to draw the structure of benzene, we can't just put one of them. We got to put both of these resonance structures, right? We have these double bonds that are changing position. Notice the difference between these two structures is just the position of these double bonds. So again, these resonance structures are just showing how these electrons can be in more than one place at one time. It's kind of common to draw benzene with just a circle in the middle there to kind of explicitly represent that as well, or again, not explicitly, but to represent the fact that those electrons are, again, kind of moving in that circle. They're sort of diffused over that entire ring there. Okay, and then again, the other thing about benzene that was killing them is they knew that there were a bunch of double bonds in there, but that they don't behave like normal alkenes. We learned last chapter, if we take, for example, cyclohexene, and we treat it with bromine, we have this addition type reaction here, right, where you get a bromine added to either of those carbons. This is one of the reactions we learned in this last chapter. Turns out, if you mix benzene with bromine, absolutely nothing happens. There's no sort of an addition reaction that occurs, right? So the bottom line is that benzene, these aromatic compounds, even though they contain double bonds, we keep them in a different category in our minds than the alkenes because they don't behave like the alkenes at all. Okay, so here are our rules for aromatic compounds. Well, let's just go. So, in order to be aromatic, you got to meet these two rules. Rule 1, a fully conjugated ring. Right, you gotta have all of these peanut-shaped orbitals all lined up, all in a row. All right, let me show you an example of a compound that would break that. If we had something like this. Again, we need that perfect spacing of double bond, single bond, double bond. The fact that we have two single bonds next to each other right here lets us know that we violated this fully conjugated ring rule. This atom right here messes up that conjugation. It doesn't have one of those peanut shapes. Again, we're looking for this pattern. Let me just redraw it because I kind of uglied it up. Double bond, single bond, double bond, single bond, double bond, single bond. It has to have that sort of pattern in order to be a fully conjugated ring. So this one, because we have two single bonds next to each other, this violates rule 1. When a compound violates rule 1, we call it non-aromatic. All right, so in order to be aromatic, you have to have a fully conjugated ring. Rule number 2 is what's called Huckel's rule. But there needs to be an odd number of electron pairs in that conjugated ring. All right, so rule number 1, it has to be a fully conjugated ring. If it violates that rule, you would call it non-aromatic. Rule number 2, there has to be an odd number of electron pairs in that conjugated ring. All right, so let's just convince ourselves real quick that benzene satisfies both of these rules, which is why it's considered aromatic. All right, first of all, we got that fully conjugated ring, that perfect spacing, double bond, single bond, double bond, single bond, right? The other thing is that we have 1, 2, 3 pairs of electrons in that conjugated ring. All right, so we have an odd number of electron pairs. So check, check, it's fully conjugated. Check, check, it has an odd number of electron pairs. That makes it aromatic. Okay? There are some compounds. So for example, this one here, cyclobutadiene. This one actually satisfies rule 1, right? It's got that perfect spacing of those double bonds. double bond, single bond, double bond, single bond. This is indeed a fully conjugated ring. But if we count the number of electron pairs, it has 1, 2. So it has an even number of electron pairs in that ring. So this one violates rule 2. Satisfies rule 1, but violates rule 2. And we call this anti-aromatic. All right, it's a little beyond the scope of this course as to why this is, the kind of explanation for this. But it turns out that just like we said that aromatic compounds have this magical added stability to them, anti-aromatic compounds are insanely unstable. They're particularly unstable, more than you would think. Okay? So again, why that is a little beyond us, but the bottom line is if you have an odd number of electron pairs in that ring, that's really good. That's really stable. If you have an even number of electron pairs in that ring, that's really bad. That's really unstable. Okay? So what we're going to do is look at a lot of compounds and apply these two rules, classify things as being either aromatic, anti-aromatic, or non-aromatic. That's the name of the game. Okay? Again, all about these two rules here. So let's look at these compounds here. Everybody take a second and see if you can't go through and figure out whether these are aromatic, anti-aromatic, or non-aromatic. And I'll get to these ones at the bottom with the little plus signs on them here. All right, so let's go through these. I guess this first one we already did, right? But we can convince ourselves again. It's step one, it's got that fully conjugated ring. And indeed, I have that perfect spacing of double bond, then single bond, then double bond, then single bond, et cetera, right? All the way around that ring. So it is indeed fully conjugated, and I have 1, 2, 3 pairs of electrons. So this is aromatic. Okay, so what about the next one here? Who thinks it's aromatic? Who thinks it's anti-aromatic? And who thinks it's non-aromatic? And who just has no idea? All right, so again, we're going to look, so this is a little bit weird because now we have these fused rings, right? We still have this perfect spacing of double bond, single bond, double bond, single bond, double bond, single bond. Same thing over here, double bond, single bond, double bond, single bond, double bond, single bond. So this is indeed a fully conjugated ring. Another thing that you can look for is each carbon should have at least one double bond, actually should have exactly one double bond associated with it, right? So every carbon in this structure has to have one double bond associated with it. So if I look at that one's associated with a double bond. That one is too. That one is as well. And I can do this all the way around, right? Each one of these carbons has one double bond associated with it, meaning it's got this peanut-shaped orbital going on. Okay, so this is indeed, even though it's two fused rings together, it is indeed a fully conjugated ring. So then the question is, does it meet Huckel's rule? We got 1, 2, 3, 4, 5. So does that meet Huckel's rule or not? Right, that's an odd number of electron pairs there, so this is indeed aromatic. And we will see big, ugly fused ring systems here. That's definitely something that we'll encounter. And again, you just want to make sure you got that perfect spacing, double bond, single bond, but also, again, you can kind of look and just ask yourself, is this particular carbon, go through, is this carbon associated with a double bond? Go all the way around. Okay, what's up?
So that double bond on the right one is also applies to the one on the left?
Say that one more time?
The double bond on the right?
You mean this thing here?
Yeah.
Yeah, so this is just a double bond between, if I got rid of all my little markings here, this is a double bond between this carbon and this carbon, right? It doesn't matter which side. If you had drawn it kind of like, I think your question is like, if I drew it like this, would that be the same thing? Right, that is indeed the same thing, right? Remember, this bond isn't associated with like one side or the other. It's actually sticking out above and below these atoms. It's this weird peanut shape where one of those peanut lobes is pointing out of the page at us and the other one is pointing into the page. We talked about the geometry of these double bonds. So benzene ring, because it's all those double bonds, it's a completely flat molecule. Right? We talked about how our alkenes had this sort of flat geometry associated with them. Because every other one of these carbons is in a double bond, this entire molecule is flat. Right? And then these peanut shapes, you got one sticking out above that ring and one sticking out below that ring. So yeah, it wouldn't matter which side you drew this line on. That double bond is indeed just between those two carbons on either side. Okay. So our next one here, I guess I did this one too. Is this aromatic, anti-aromatic, or non-aromatic? Non-aromatic, right? So we got and this one, and this one, and this one. They're all associated with double bonds. But then we have this guy here that completely messes it up. Instead, this is bound to two hydrogens here. It doesn't have one of those little peanut-shaped lobes. So it breaks the ring's conjugation. So this is anti-aromatic. All right, this is a 7-membered ring here. Those are a pain in the butt to draw correctly, but nonetheless, get good at our shapes here throughout the semester. Who thinks this one's aromatic, anti-aromatic, and non-aromatic? So indeed, this one would be non-aromatic. If we're going to go through and ask ourselves, okay, this one, all right, these are all perfectly spaced. They're all associated with a double bond, but then again, I get to this one, and it messes up that ring's conjugation. There are just two hydrogens here. So this is whoa, my bad. This is non-aromatic. Just like this one is non-aromatic. My bad. Also can't spell. Right, both of these compounds violate rule 1, making them non-aromatic. All right, we also did cyclobutadiene. We said that even though that has this perfect spacing, it's a fully conjugated ring. It only has 2 pairs, and thus this is anti-aromatic. All right, so now we have these ones with this positive charge here. So how do we deal with that? What do we call a carbon with a positive charge? A carbocation. So one of the things that we talked about with carbocations is that they have how many bonds? Should be 3 bonds and no lone pairs. So it turns out that the shape of a carbocation, it's missing a pair of electrons, right? Carbocations are kind of weird compared to like oxygens when they have a negative charge or nitrogens when they have a negative charge, in that they only have 6 electrons in their octet. So they're missing a pair of electrons. That missing pair of electrons lives, well, I guess it doesn't live anywhere, results in an empty p orbital, right? So carbocations have this shape where they have this p orbital that just doesn't have any electrons in them. So they actually don't mess up our network of conjugation here because they also have that p orbital associated with them. They don't have any electrons in them, but they don't mess up our ring's conjugation. So if we sort of looked at this molecule here, and again, I'll sort of try to draw it even though it's going to be terrible. There's this p orbital, peanut-shaped orbital here, and a peanut-shaped orbital here. We know that because of the double bond between those 2 carbons. But this carbocation also has that peanut-shaped orbital there. It's just empty. But it doesn't mess up the ring's conjugation. Okay? So this is indeed still a fully conjugated ring. These 2 have their little peanut shapes, and so do carbocations. Okay? So importantly, we can make a note here. When we're sort of talking about rule 1 here, carbocations do not mess up a ring's conjugation. All right, when we're going through and saying, is this carbon in the conjugated with this one, with this one, with this one, we can include those carbocations as well. All right, they turn out to have a p orbital that's just empty. So then looking at this one here, this one does not violate rule 1, right? Again, that's my whole shtick that I'm getting at here, is that this particular compound, even though it has that carbocation there, it does not mess up the ring's conjugation. It is still a fully conjugated ring. Check, check, satisfies rule 1 here. So then would this be anti-aromatic or aromatic? This would just be aromatic because there's only 1 pair of electrons, right? That carbocation doesn't have any electrons associated with it. So there's just 1 pair of electrons here, an odd number. So this would be aromatic. Okay, so then given what we just discussed, everybody take a second and see if you can't classify this last one for me. All right, so who thinks it's aromatic? and who thinks it's anti-aromatic? All right, so first let's just convince ourselves that it actually satisfies rule. I guess there was a third option, non-aromatic. But let's convince ourselves that it is indeed a fully conjugated ring. I'm gonna look, this carbon is a part of a double bond. So is that one, so is that one, so is that one. And again, this positively charged carbocation does not mess up my ring's conjugation. So all of those carbons in that ring are indeed conjugated. All right, now I got to go through and count pairs of electrons. We got 1 here, 2 here, right? That carbocation doesn't have any electrons that it's bringing to the table. So there is an even number of electrons, pairs, making it anti-aromatic. Okay? So real quick, we were talking about for rule 2, you're counting pairs of electrons. If it's odd, that's aromatic. If it's even, that's anti-aromatic. You also hear this called the 4n+2 rule, right? So that you can either talk in terms of pairs of electrons or actual total number of electrons, right? So if we are going to look at benzene and we said that there are 3 electron pairs, how many total electrons are we talking about? If each pair represents 2, that would be a total of 6 electrons, right? So kind of how it was taught to me back in the day was this like 4n+2 rule where you're talking about the total number of electrons. To be clear, what the heck does that mean? So 4n+2 is really like a shorthand for, it's not a math problem where you're like solving for n. It's just shorthand for a series of numbers where you plug in increasing integers into n. So if you plugged in 0, that would be 2. If you plugged in 1, that would be 6. If you plugged in 2, that would be 10. If you plugged in 3, that would be 14, etc., etc. You can get this like series of numbers. If your compound has that many electrons total, then it's aromatic. Okay, so that's this 4n+2 rule. You can either talk in total number of electrons or electron pairs. Again, it was kind of taught to me, this 4n+2 rule, but over the years I realized that students kind of like the odd or even rule a little bit better. It's a little bit easier to wrap your head around. Nonetheless, you'll sort of hear both of them, all right? And again, 4n+2, you're not talking about like a math problem where you're solving for anything. It's just this shorthand for this series. Either 2 electrons, as was in this case, would be aromatic. 6 electrons, as in this case, would be aromatic. 10 electrons, as in this case, would be aromatic, right? So you can either talk in electron pairs or total number of electrons. They're kind of one and the same. All right. So now we got to complicate things a little bit here. In terms of, okay, so let's say we had this compound here. Oops. It had a positive charge on this carbon. Okay, I gotta redraw it. It's gonna drive me nuts. Again, we said this was anti-aromatic. All right, but what if instead of a positive charge, we had a negative charge on that carbon? Again, the positive charge, we call those carbocations. Anybody guess what we would call a carbon with a negative charge? Yeah, carbanion. Okay? So now we have this pair of electrons. So what we're going to see with our lone pairs is that they can kind of like decide whether or not, obviously they don't really decide. They don't have any sort of like, free will or anything like that. But that's kind of how I think about it. They can either decide to participate in the ring or not. And they're only going to decide to do so if indeed it would make the ring aromatic. Okay? So in this case here, I would look. I would say that these are all conjugated with one another, right? They got that perfect spacing going on. Does this one count? It will only count if it makes that ring aromatic. All right, so this ring as it stands has 2 pairs. If it included that lone pair there, that would take it up to 3 pairs. So is that good or bad? Good, right? Odd number is aromatic. So indeed, this would be an aromatic compound. Okay? This carbon here, it can decide whether or not it wants to put that lone pair in a P-shaped orbital like this, which would have it participate in the ring, or it can put it in a different shaped orbital and not participate at all. And it's only going to decide to put it in that P orbital. It's only going to decide to put it into the ring if it makes that ring aromatic. All right, so let's look at the flip side. Try my best to draw 7-sided. It's as good as it's going to get. Okay, so first, I want everybody to take a second and tell me whether this compound here is aromatic, anti-aromatic, or non-aromatic. For this one over here, who thinks it's anti-aromatic or non-aromatic? Who thinks it's aromatic? Yeah, so indeed this one would be aromatic because we have this perfect spacing of our double bonds, but then again, that positive charge, it's not going to mess up our ring, so we get to include that as well. We go through and count the number of pairs of electrons, and there's an odd number, so this is indeed an aromatic compound. Okay, we go on to this example here. All of these ones are conjugated. The question is, what happens to this lone pair here? Again, it's only going to let that lone pair play with its friends in the ring, participate in that network of conjugation, if it would make this compound aromatic. If that pair of electrons was in this ring, would that compound be aromatic or anti-aromatic? It would be anti-aromatic if you included that pair of electrons. So what happens is, this carbon atom right here, instead of putting that pair of electrons in a P-shaped orbital, it just puts it in a different shape. So it breaks the conjugation of the ring. It's not going to be anti-aromatic, right? Because anti-aromatic's bad. Instead, it's just not going to put it into the ring. It's not going to let it participate in that network, making this one non-aromatic. So when you have these lone pairs, it's never going to be anti-aromatic. It'll either be aromatic because that pair of electrons is allowed to participate in that ring, or that atom's just going to pull it out of the ring, not let it be in there at all, making that compound non-aromatic. Holy crap. Get it all straight. Okay? So, and just to sort of illustrate what that looks like here, here's another example, but now instead of having a carbanion ion, I have nitrogen. Nitrogen's got a lone pair, right? So this is something we're going to see with what are called heterocyclic rings, or rings where you have nitrogen or oxygen in there as well. So here again, we can play this same game where we're going to ask ourselves, is this aromatic or non-aromatic? We have these carbons that are all conjugated, and then we have this lone pair that we got to decide. Is it going to participate or not? In this case, if it puts that pair of electrons in that ring, that would indeed make it aromatic. So it's going to do just that. And so if you looked at these sort of p orbitals in this molecule here, again, we have our normal, these ones. Let's actually color code here. we have all of these carbons. So they all have their p orbitals, all right, sticking out above and below that ring. Again, this kind of illustrates how these aromatic compounds, they're flat, right? So these p orbitals are sticking out above and below those rings. And this nitrogen gets to decide whether or not it's going to put its pair of electrons in the ring. Because it would make it aromatic, it indeed sticks them in one of those peanut-shaped orbitals, right? Allows it to be in that fully conjugated ring. If not, it would just stick it in a different shape. All right, that pair of electrons would be sticking out. I mean, again, I'm not an artist, but let's say that this wasn't the case and it would make it non-aromatic. It's just going to put that pair of electrons in some sort of an orbital that's like sticking out over here or something, right? Just isn't lined up perfectly with all those other ones. All right, so we're going to go through now and again sort of just look at some examples, and we're going to figure out whether they're aromatic, anti-aromatic, or non-aromatic. And we're going to mix in some with lone pairs like what we saw. Let's do... All right, so let's say one is non-aromatic, 2 is aromatic, and 3 is anti-aromatic. Everybody, show me with your fingers. What do you think this first one is? 1, 2, or 3? All right, so indeed, first of all, this one, if we start looking, making sure that everything is conjugated, we got this one all with our perfect spacing. But then we get to these ones that don't have, these carbons don't have any double bonds associated with them, right? So this now breaks up my aromaticity, making this non-aromatic. All right, what about this big ugly one here? 1, 2, or 3? What do we think? Okay, so again, let's go through and make sure, see if we have our fully conjugated ring. Okay, I'm going to look. Is this carbon associated with a double bond? Check, check. What about this one? Check, check. This one. This one. This is also associated with a double bond. So is that one, right? So is this one up here? All of these are indeed associated with a double bond. So this is a fully conjugated ring. You can just convince yourself that every color purple that I just put down right now, there is one double bond attached to that carbon. Right? So it's got that p orbital going on, sticking up above and below that ring. So indeed, this is a fully conjugated ring. So then I can go through and just count pairs of electrons. 1, 2, 3, 4, 5, 6, 7. That's an odd number of pair of electrons. So this is indeed an aromatic compound. All right, what about this one? What do we think? 1, 2, or 3? Non-aromatic, aromatic, or anti-aromatic? No guesses. All right. So, first of all, I got to go through. These ones are carbons that are associated with a double bond, so they're all conjugated. But then I got to look. This one has this lone pair here, right? So then I got to ask myself, is this lone pair going to want to participate in the ring or not? If it participates in the ring, that would make it, it would only do so if that makes it aromatic, right? So in this case, we already have 1, 2 pairs of electrons. So if that lone pair participates, that would indeed bring me to 3. So this would, so it's going to put them in a p orbital. So this compound is aromatic. Okay. Now, oxygen, unlike we did an example with nitrogen previously, oxygen actually has 2 lone pairs here, right? Only 1 lone pair can participate. In the ring. All right, it's impossible for oxygen to arrange its electrons in such a way that both of those electron pairs are in that ring. It would have to put them both in kind of the same shaped orbital and everything like that. It can't do it. It violates a bunch of rules about how electrons are. They can't be in the same, those 2 lone pairs have to be in different orbitals. Can't put them in the same shape, right? So it can only ever put one in the ring. The other one's just gonna remain a lone pair. But again, it's just like nitrogen or the carbanions that we saw. It gets to decide whether or not it wants to put it in the ring, and it's only going to do so if it makes that ring aromatic. All right, so now we have a similar situation here where we have, these are conjugated, but then we got to ask ourselves, is that pair of electrons going to want to participate in that ring? No. In this case, is it? No, right? Because that would bring me to 4 or to 2 pairs of electrons, so instead, is it anti-aromatic or non-aromatic? Non, right? It's never going to be anti-aromatic with the lone pairs. It's just not going to put the pair in the ring. It's going to break the conjugation, making it non-aromatic. aromatic. All right, what about this one here? So this one's a little funky in that if we look, all of our carbons are indeed associated with a double bond. These are all conjugated with one another, right? But does it violate rule 1 or no? Yeah, because again, it had to be a fully conjugated ring in order to be aromatic. So these are actually conjugated double bonds. The electrons will diffuse, but they won't be in that magical ring thing that makes it aromatic. So because there's no ring, this is non-aromatic. All right, what about this big ugly thing down here? Is this non-aromatic, aromatic, or anti-aromatic? 1, 2, or 3? Does anybody have a guess? Nice, yeah. So, again, we just got to go through and look at each carbon and convince ourselves that it is indeed going to participate in conjugation here. Do they have a double bond associated with them? So indeed, boom, 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 boom. All of those carbons that I just highlighted have a double bond associated with them, meaning they have that P-shaped orbital that can allow the electrons to move about, right? But then I got this lone pair here. So again, in these situations, I got to decide, is that lone pair going to participate in the ring or not? And it's only going to do so if it makes the compound aromatic. So I'm going to go through and count what I already got. 1, 2, 3, 4. So is it going to participate or not? Yes. Yeah, because that would bring me up to 5 pairs of electrons. So indeed, that would make this compound aromatic. All right, and then lastly, this one here. I did a terrible job drawing it, but it's like two pentagons that are fused together here. 2 5-carbon rings. Is this going to be non-aromatic, aromatic, or anti-aromatic? 1, 2, or 3? What do we think? Nice, yeah. So indeed, if we look, again, we got to convince ourselves that the ring is fully conjugated. So we look, each of these carbons is indeed associated with a double bond. So it doesn't violate rule 1. But then I go through and I count pairs of electrons. 1, 2, 3, 4. I got an even number of pairs of electrons, so this would be anti-aromatic. Okay? So that's sort of the name of the game. We want to be able to classify compounds as aromatic, anti-aromatic, or non-aromatic based on these 2 rules here. If you violate rule 1, you're non-aromatic. If you violate rule 2, you're anti-aromatic. And if you satisfy both of them, you're aromatic. Cool.